In section 7.2, we start looking at different types of solutions, and I'm going to focus on different types of aqueous solutions. And so these are going to be solutions where water is the solvent. And in particular, I'm going to look at what happens when an ionic compound dissolves in water. And let's just use the example of sodium chloride. When sodium chloride is dissolved in water, what we'll see is that the crystalline sodium chloride separates and forms sodium ions and chloride ions. Now, if I take an acid, which as we know is a class of covalent compound, acids have this feature that when they are dissolved in water, they separate to form one or more hydrogen ions and an anion. So some substances, when they are dissolved in water, will separate to form ions, positive ions called cations, negative ions called anions. However, most molecular compounds, all of those that are not acids, and a good example of this would be a compound called methanol. It's a liquid. If that is dissolved in water, all that happens is that the molecules kind of separate from one another and disperse throughout the water. So we end up with just the molecules dispersed throughout the solvent. So this gives rise to different types of solutions, some that contain ions and others that contain neutral molecules. So when an ionic compound is dissolved in water, what happens is that there are some attractive forces between the water molecules and the ions, and basically the ions get ripped off the surface of the crystal and then dispersed throughout the water. So that's kind of cool, right? So the water molecules are kind of like grabbing at the surface of the crystal and they just kind of like tear it apart. But the important thing is that what we end up with is individual sodium ions, in this case because it's sodium chloride, individual cations and individual anions dispersed throughout the solvent. Now, it turns out that some ionic compounds are really soluble in water. These are the types of things that we're going to see in the ocean, right? Because when it rains, they just get washed into the ocean. Other ionic compounds are not very soluble in water. The attractive forces holding the crystal together are too strong for the water to tear apart, right? And we're going to find those ionic compounds on the surface of the earth, on the solid part of the earth, rather than in the ocean, because when it rains they don't end up getting washed into the ocean. So sodium chloride is kind of our go-to soluble ionic compound because it's very very soluble, and it's and for this reason known as sea salt, because it kind of it's found in the ocean. It's one of the major ionic compounds in the ocean. Now there are some sort of debate about when do you declare something to be insoluble, and for us we're going to say that something is insoluble if its solubility is less than 0.01 mole per liter. Okay, so as I mentioned in the introduction, when ionic compounds are dissolved in water to form aqueous solutions, the compounds dissociate into their component ions. The crystal just gets ripped apart. And so what this means is that solutions of ionic substances in water are able to conduct electricity. Now, the electrical conductivity results from there being mobile charged particles. And that's exactly what we have here. We have sodium ions and chloride ions that are just able to freely move around. They're not bound up in a crystal. And solutions that are able to conduct electricity are referred to as electrolytes. So when ionic compounds are dissolved in water, they form electrolytes, which are solutions able to conduct electricity. And the reason that they're able to conduct electricity is because we have mobile cations and anions. So we can kind of see this. If we just have a sample of distilled water, that won't conduct electricity. Water is not electrically conductive because all we have present are electrically neutral water molecules. And we need mobile charged particles in order for something to conduct electricity. Now, if I have a sample of solid sodium chloride, a solid ionic compound, that also won't conduct electricity because the cations and anions are bound in a crystal and they can't move. They are locked in place, so there are no mobile charged particles. But however, if I dump the water into the ionic compound, then the water tears the ionic compound apart and I have individual positive ions and individual negative ions that are able to move around freely, and sure enough, the aqueous solution will conduct electricity. It will behave as an electrolyte. Okay, now what about if I have just a pure covalent compound? Well, some covalent compounds are soluble in water. And a good example of this is an alcohol here. It's called ethanol. That's the alcohol that gets you drunk. It's a liquid. And if you dissolve that in water, it doesn't separate out into ions. The molecules that make up the ethanol just kind of separate from one another and end up dispersed throughout the water. So when covalent compounds that are not acids are dissolved in aqueous solution, we don't end up with any charged particles. We just end up with molecules that are kind of a little bit separated from one another. So covalent compounds don't separate into ions unless they're acids, that when they're dissolved in water, they remain as intact neutral molecules. And for this reason, because there are no mobile electrically charged particles, they do not conduct electricity, and we classify these kinds of solutions as being what we call non-electrolytes. Now, it turns out that some covalent compounds, they're acids, but they're not like what we call strong acids, where 100% of their molecules fall apart into cations or hydrogen ions and an anion. They're what we call weak acids, and only a few of the molecules dissociate in this way. And a good example of that is acetic acid, which is the acidic component found in vinegar. And if I take a sample of acetic acid, dissolve it in water, a few of the molecules separate into hydrogen ions and the acetate anion. It's what we call a weak electrolyte because it's going to weakly conduct electricity because there's just a few ions around. Now, of course, strong acids, and these are most of the acids that we've found, that we've seen, they completely separate into hydrogen ions and an anion, and they're going to be good conductors of electricity. But I think what I'm really kind of stressing here is that the only time we see any electrical conductivity is when the act of dissolving the substance in the solvent results in the formation of mobile electrically charged ions that are able to move around. If we don't get that, then it won't be able to conduct electricity. If we have a lot of these ions, it'll be a good electrolyte. If we have only a few, it's going to be a weak electrolyte. Okay, so we've looked at the different types of solutions in terms of whether when the solute is dissolved into water, does it separate into anions and cations, or does it remain intact as molecules which are electrically neutral? We can tell whether we are generating ions when a substance is dissolved in water by whether it generates an electrolyte, which is a solution that is able to conduct electricity.